hopefully you all got the Elixir One lab in on Friday. If not, try to get that in soon because the Elixir 2 lab is, but by design, meant to be a bigger thing. It's not a huge amount of code that you're actually having to write for it. We give you all of the gen servers for it, the main workers for it. You're again going to be, you'll write the name server, which uses the gen server behavior. Then also you're going to create a supervisor tree. That means you're going to create multiple supervisors. So the key is to look at the dependencies and realize, okay, in fact, I would actually sketch out a dependency graph and then look at that structure, and that's pretty much going to give you the structure of the supervisor tree. So remember, a supervisor will supervise one particular set of workers with a particular restart strategy. And if you sort of have one set where these need to be restarted with one strategy and these with another, create intermediate supervisors for each one, and then another supervisor. So look at that and try to look at the structure of what could be grouped into the different restart strategies that we've talked about. Remember the one for one goes down, one comes up. Rest for one goes down, all for one, I may have that backwards or what. Anyway, one goes down, the whole set goes down. Then rest for one goes down, and only those in the rest of the dependency chain go down and get restarted. So the key thing is just really thinking through that. It should not be a huge amount of code. This is not lots and lots of code. It's just you have to think through exactly and understand that gen server and supervisor behavior. Remember that the Elixir 2 lab is due on this Friday. Any questions on that lab from anybody who started yet? Yeah?
Just general. What's the difference between .ex and .exs?
I may have mentioned that before, but Elixir can be compiled. So it's intended to be compiled, but it can also run in what's called a scripting mode, which is basically it pre-compiles it under the hood for you and then runs that. So it looks like it's scripting and running interactively. So .ex is sort of your regular Elixir files that are compiled. .exs indicates ones that are meant to be run in scripting mode. But you can use either way with this. Yeah.
So with Elixir 2, it gives us a lot of sample code, but where do we really get started? Are we coding, like importing that, or?
Yeah, so we actually give you, if we actually look at the assignment here, so you'll see how it has 6 modules. These are the different workers. That code we give you is not just template, that actually is the code for those different ones. So you shouldn't have to modify those. What you need to do is to implement the name server and then the multiple supervisors making up the supervisor tree.
Okay.
So if you go over to, yeah.
So there's other modules that we're writing, and we're not touching any of the code for the ones that have already been written.
Yeah, you shouldn't need to modify any of these.
Okay.
Right? What you'll need to do, and then Crasher's thrown in there because it's designed to sort of crash a particular module. And so, yeah, all of this is given for you. And what you will do is you will add the supervisors. You will add, so you will define a module. The form of a supervisor will be define module, def module, module name, do, use supervisor, and then follow the example that we went over in the slides for setting it for a supervisor. And then the name server will be another gen server. So it'd be def module, name server, do, use, gen server. And then that, in the assignment, we specify exactly the messages it needs to handle.
Okay. So it's just those 2 modules that we're writing then?
So you'll have multiple modules for the supervisor tree. So there's 2 parts. There's one module for the name server. That is just one module.
Okay.
The supervisor tree, though, if you actually go down here, this is what I meant by sketch out the dependencies here. So for example, you'll notice that there are a lot of things that depend on the database. But let's see, you'll have other things that order depends on user depends on order, so maybe that might be a one-for-all group, where one goes down, the other, anything else in the group also goes down, not just a sequence. So if you sketch that out, you'll see an idea of how you can then structure the supervisor tree around the different restart strategies. So, but that one might be a few different supervisors that you have to write. Ultimately, there'll be one root supervisor. Yeah.
Can you have multiple supervisors pointing to the same module?
No, because each one would sort of spawn off a worker. So typically, every worker has one boss, so to speak. Maybe it's the whole serving two masters thing, I'm not sure, but no, it actually is a lot clearer if it's part of just one pool.
Mm-hmm.
And then what you should, and then there's code given to you for how to start it up. So you'll start up the name server. That really should be called name server. Your top level supervisor should be called top supervisor, but we don't specify the names of any intermediate ones. Just the top level supervisor and then the name server are the ones that we specify the names for. So you start things up like this, and then this is the way that the TAs know how to start it. The top supervisor, by the way, would start up any workers it directly supervises, but it would also start up any sub-supervisors. Does that make sense? And then they would do the same kind of thing and so on. And then what you should see is if you invoke, so when you start up the top supervisor, you should actually see all the different modules. If you look at the code that we give you, each of them when it starts up reports that it's starting up, so that you can see when it starts up, but also when it restarts. So when you start the top supervisor, you'll see them all start, but then if you start killing off particular ones, so if you say crash the order module, then Crasher says it's crashing that module, and then you'll see a bunch of restart messages. So if we crash order, order should restart. But you'll notice, remember I said order and user are mutually interdependent? And so you crash order, user and order both restart. Make sense? The exact order, that's non-deterministic, I believe. Because there's all kinds of race conditions that you can have in terms of starting up on different processes. Questions? Okay, I hope that time was helpful for laying a groundwork for getting started. Yeah.
So we're only supposed to have one module per file, right?
Well, in this one, we actually give you one big module
Okay.
that has all of it. So you can actually put all of this in one if you wanted to for this one.
Okay.
Or if you wanted to break it out into separate ones, that's okay too.
And so for the one that we're writing then,
Right.
you wouldn't
You-
include
you
it in
could-
yours?
You could just put it in here if
Okay.
you wanted to.
Okay.
All right. In fact, I'm trying to think if we actually specify that or not. We probably should, yeah, emphasize you don't need to modify that code that we give you. Construct a module. I'll double check with the TAs and seeing if there's a form they would want it to come in. Otherwise, just plan on putting it in the same one.
Okay.
All right. So what we're going to do this week, today and Wednesday, we're going to continue talking about garbage collection. By the time we finish today, actually, I hope, you'd have enough to start on the garbage collection lab. So the garbage collection lab is not a coding lab, I mentioned that before. It's, I'll take some time later to go over it, but it's simply a spreadsheet, and we use that to give you the information, because a spreadsheet's a nice way of giving you, here is a heap, here's the address, here's the contents, and so on. You're then going to fill in, you're going to play algorithm for different kinds of algorithms. And you'll fill in, so remember we talked about mark and sweep? You'll fill in, what does it look like after the mark, what does the heap look like after the mark phase? What does it look like after the sweep phase? Today we're going to be talking about another technique called stop and copy, where you're going to be showing here's the before and here's the after. So you'll be doing that for both mark and sweep and stop and copy. It should not take very long at all. Once you actually understand the algorithms, it's something you should be able to sit down and do in less than an hour. And so that's nominally listed as being due next Wednesday. This is not meant to be a suggestion that I expect you to be working on this the day before Thanksgiving. This is simply, once you finish Elixir 2, finish this, get it done before you take off for the break. And this is, putting the deadline here is just simply my way of saying any time before Thanksgiving is just fine. Okay? It's not a suggestion as to when to do it.
So
Yeah.
this sounds more like a homework assignment rather than like a coding lab?
Yeah, it's not coding at all. It's more one of those homework, play computer.
Yeah.
Yeah. You might have, I mean, you probably had this before, where here's such and such an algorithm, show the intermediate
Yeah.
steps as it's doing its thing. All right, so let's get to these different techniques. I want to go back, pardon me. So we talked at the end last time about mark and sweep. Remember, the idea is we talked about the root set, all the named entities. So you'll start at the root set, you'll traverse out from the root set to see what's ultimately reachable. And that's done in a depth first traversal. Sorry. Excuse me. I think I might be starting to get
Where root set is just like the start, the very first thing you.
Yeah, so if you think about, well, not necessarily, no, it's not the first thing you allocate. It's the named things. So in our interpreter would be the environment, and parent environment, and parent and so on. In other things, it's basically, if you think about how you're going to access data, you start with an identifier. Okay, so you start with a variable name. Other than maybe a few things that are sort of in flight, maybe they're just being created and passed. And those are typically, in a compiled language, would be stored in current registers. So you start with that root set. So you clear all the marks, you start with the root set, you traverse outward marking everything, and then you have the sweep phase. So there's the mark phase and the sweep phase. Sweep phase, then, you're going through and you're basically saying anything that didn't get marked during the traversal out from the root set must not be reachable from the root set, so we can safely reclaim it. And then we basically just go through marking those blocks as free, linking them into the free list, and so on. When you do this with the assignment, you'll find that the tricky part is actually updating that free list to make sure that you actually have the appropriate, that still now shows up in the free list. Remember, the free list is, you have all your free blocks. They might be fragmented. We're going to come back, and that's where we'll mainly pick up today. Those might be fragmented, and so you have to keep a linked list of them in any order. It doesn't have to be in sorted memory order. But there's no additional magical memory somewhere else to store stuff. The only memory you have is the heap, and so you can you have to actually store that free list in the headers for each of those free blocks. So each free block should have, and in the assignment we give you the structure of the header. Every header for a free block should include the address of another free block, except for the very last one, which you can null terminate. Or you could put any other you could put -1 or something else, whatever you want to use to indicate that there is no more in this free block chain. So you mark, we sweep, and we collect garbage this way. Notice again, there's an explicit on-demand collection phase. So typically, remember we talked about how the garbage collection system, or the memory management system, is allocating things to the program as requested, or to the user's program. It's managing the heap, and then when it gets a memory request that it can't satisfy because there's no more free memory, it then kicks off a garbage collection pass. And that's what mark and sweep does. So it's in that on-demand phase that the mark and sweep happens. And then you come back, you retry the user's request, because hopefully going through garbage collection freed up enough memory to satisfy their request. So what we got to last time is the problems with mark and sweep are fragmentation. You can have lots of blocks that are still in use and a whole lot of free blocks scattered in between them, to the point where there may be a large percentage of the heap that's still free, and you can't satisfy even a modest sized memory request because there just isn't a single coherent block that's big enough. Some other issues, and we'll look at this. So remember our goals, I didn't write them this time, were, actually let me put them here so we can come back to them. Remember the goals of garbage collection. Soundness. Never throw away anything the user could use. Mark and sweep is sound. Utility. Mark and sweep is really good at utility because it'll find things like those cycles and things that reference counting wouldn't do. But there's the efficiency issue. Actually, you can factor fragmentation really under utility. So it's collecting it, it's marking it free, but, and by the way, again, whenever you have adjacent free blocks, you coalesce those together. That helps with the fragmentation somewhat. But even then, you're not really making optimal use of your memory because it's fragmented. Some other things in terms of efficiency. The cost is proportional to the size of the heap. So you have to go out during the mark phase and visit everything that's live. But during the sweep phase, you're actually visiting everything live and dead. Okay, so the total number of objects is in essence the amount of work. You have to visit everything that's been allocated, whether it's still in use or not. That, of course, also means you're going through your memory, touching everything, which completely destroys your memory caches and anything else like that, and also can trigger a whole bunch of virtual memory paging. So these are all potential issues with mark and sweep. So I suggested at the end last time, and I think this is where we left off, that you could do a variant of mark and sweep is called mark and compact. So the idea is the same way you guys have seen before with things like disk defragmentation programs. We'll actually move data on the user. So when it goes through, let's see if we see this in our illustration, we should see a bunch of, as it goes through freeing things, let's see, they're triggering us up a pass. But notice it's actually moving all the stuff up to the heap. So you go through and you do the same mark that you normally would do. But during the sweep phase, you go through and you identify free blocks. And basically, you just slide them up to, every time after you go through and you mark everything free, and then you go through and make another pass where you take every block and say, is the block before me free? In which case, I'm just going to slide it up. And everything slides up to the top of the free block that's on top of it. So when you're done, you have one coherent free block. No free block list. There's no free list. The nice thing about not having any free list is, first off, you don't have to maintain all that. Allocation becomes really straightforward. You don't have to search through a list of free things trying to find one that's big enough. There's only one, and it's as big as you have. So it avoids the fragmentation. Now, it turns out that to do this, though, you actually have to make multiple passes. You have to make a pre-pass first to figure out where everything's going to move to. And then, because what if those blocks have pointers? All right, so actually, let me back up to a different issue first. So, as a C programmer, does that make you a little queasy to think that it could be moving memory around on you without telling you? Okay. Part of it's because you have the ability to have explicit pointers and manipulate them as you will. But think about something like Java. You simply say this variable name equals new such and such, and it allocates it, and you know that there's some pointer under there, but you can't really get your hands on it. Well, if it moves a block around, but at the same time it goes back and updates the variable that says, oh, that's actually stored here instead of here now, do you really care? Because when you come back to that named variable and you access the object that it points to, okay, it's moved, but it's still pointing to the same object, just at a different spot in memory. Does that make sense? So this is one of the big advantages of doing this at the program language level, is it can move stuff around on you, and as long as you update your root set that says, oh, this thing's stored here and this thing's stored here, you're fine. Now, the other thing, though, is you have to update every allocated block that could have pointers to other allocated blocks. Those have to be updated too. And there's the real trick when you're doing what are called copying collectors like this. You have to actually update all those pointers as well. So what Mark and Compact will do is it will make one pass through first, figuring out where everything's going to go to, but not moving it yet. Okay, disk defragmentations usually do that too. You make one pass through figuring where everything's going to move. Then you make another pass through, and you're actually moving it and updating the addresses with the root set. But also, as you move a block, you look to see, oh, are there any pointers in this block? What's the new address of where what it used to point to will now be at? If you understood what I mean by that. So where is the thing pointed to by that going to move to? And you update the pointer. Even if you haven't copied that yet, you've already made this pass through to figure out what all the updated pointers will be, and then you update them as you're doing this sliding for the compacting. Make sense? But it's a lot of work. And it also means not only do you have to make one pass through everything, you're making multiple passes through everything, okay, in terms of memory caches and virtual memory and stuff like that. So, yeah.
It seems like if you were using a lot of your memory, this would be really bad or really inefficient. Or would it just not have to slide stuff around as much?
Yeah, and that's a really good point. If a lot of memory is still in use, then you're moving a lot of stuff around. And yeah, then this starts to become a drawback. The main reason, of course, that you're trying to actually compact things is to get rid of fragmentation. Now, it turns out, and time permitting on Wednesday, we'll mention some actual statistics. In a lot of languages, where you're allocating things and deallocating all the time, it might be that by the time a garbage collection pass kicks in, 90% of the heap might be dead.
Okay.
In which case, okay, I'm willing to spend the time moving around the 10%, so I have defragmented memory for later use. Okay. Yeah.
So what does that make the big O for this?
So basically, it's order the number of objects in the heap live or dead at the time of the garbage collection pass. So mark and sweep, it's 1 times that. This basically turns out to be 2 times that, because you've got to make multiple passes through, but that's still the same in a big O sense. You guys all know, of course, big O ignores constants, but when you're sitting there waiting for your program to finish running, those constants actually matter. So if it goes into, remember we talked about how sometimes you'll get a pause in the execution of your program while garbage collection is kicked in? Well, this could mean twice as long a pause, potentially. Actually, it's typically a little bit worse than that, because you're not only having to actually visit all the blocks, when you actually move, you're not just reading things and maybe marking a few locations, you're moving whole memory blocks. So now you have memory writes, so you've got, you just got more reads and writes of I/O to your memory, which is slower than just sort of a straight computation. All right. All right, so again, we kind of talked about this. Sorry, I got ahead of myself on the slides. Start by marking live objects. They're all compacted, just slide them down. Notice you, let's see. The big thing is new objects can be allocated efficiently, and that's where you're getting the defragmentation. And again, you're having multiple passes here through it. These last two can actually be combined sometimes. All right, so let's talk about another way, another type of algorithm. So if you're following along on the slides I distributed, this is the ones for today. There's another set of approaches called stop and copy. And time permitting, we'll get to what are called incremental collectors as well. So remember, the whole point of going from mark and sweep to mark and compact was getting around or the memory fragmentation issues. So stop and copy is designed to do the same kind of thing. It's been around for a while. Also, quick history thing. Garbage collection systems first actually appeared in Lisp. This idea of automatic garbage collection has been around for a long, long time in Lisp and its derivatives. Okay. And it was only later then picked up by lots of other things, including Java. A variant of stop and copy is actually what you'll find in most Java implementations. The reason I say most is, do you know exactly what algorithm your Java virtual machine is doing? And more importantly, do you care?
It works right.
As long as it works right, right? It's transparent to you as the programmer in the language. So stop and copy is also trying to avoid fragmentation issues. Now, it turns out, so I asked before, you've all run disk defragmentation programs, or you've at least seen them or the concept, right? How long do they take to run?
Forever.
It's like the kind of thing you go to bed and you leave it running overnight kind of stuff. Turns out there's actually a much, much faster way to defragment your disk. Okay? Turns out there's also correspondingly a much faster way to defragment your memory than the stop and copy, or the mark the mark and compact kind of approach. Most disk defragmentations work a lot like what I just described for the compact phase of mark and compact. You're making multiple passes through where are things moving to, updating pointers and other stuff, and then actually copying things. Turns out there's actually a much, much faster way to defragment your disk. Here's what you do. Go buy a second disk that is just as big, reformat it, copy all of your current data that you care about from your old disk over. And so one thing that happens with that is you only have to actually copy the files that you care about. Right? It's a good time to actually throw away stuff you're not using. And they're automatically all together contiguously with one big defragmented rest of the disk. And it's much, much faster than sitting there trying to copy things back and forth. You ever sat and heard a hard disk chatter while you're running those disk defragmentations? Yeah. So it's a lot faster. And by the way, when that one fills up in fragments, what do? You take that first one you had, wipe it, and repeat the process back. And that's in essence what stop and copy is going to do. So we're literally going to, now we don't necessarily have a second heap. But there's a lot of different ways you can do this. One is, so we're going to literally think of two heaps. One that during collection, we're going to copy from one to the other. So these are called semi-spaces in garbage collection terminology. One is the from space, that's where all your stuff currently lives. And the to space that starts out empty, that you're going to copy all your currently live data to. Okay? Anything that doesn't get copied over, it's just freed. I don't have to actually do anything. It just doesn't get copied over. Now, this could actually be, the simplest way to do this is actually take the total amount of memory allocated to you from the operating system and cut it in half. Now you might think, oh, wait a minute, the whole point of garbage collection is to be efficient, right? Well, in other words, make efficient use of your memory. But it turns out that really efficient use of half of it might be much, much better than totally fragmented use of all of it in terms of the type of memory you can allocate. The other thing is I could do things where maybe I actually request a new chunk of memory from the operating system, I copy it over, and then I return this back to the OS. There's all kinds of strategies you can use that way. The key thing, though, is we're going to have a from space and a to space. So during collection, you'll notice this is quickly going to fill up. It's just going to start copying to this sort of second half. It only copies the live data. Right? So this is and then as soon as you copy over, they switch roles. So this now is the current space where I'm allocating stuff. As that continues to allocate, it will eventually it'll get copied over here. And you'll notice it's just a back and forth, copying of only the data, only the live data. Yeah?
Well, why is it copying? Because I don't see like any improvement in the stack before.
Oh,
and
in
stack
this case,
after.
I think it's also set. So I said there's on-demand garbage collection. Some you can also configure to trigger and run periodically, just automatically trigger collection in anticipation of future allocations that are coming in terms of defragmenting.
Because like we're talking about like stopping and copying everything you have to a different place.
Right.
But I don't see why you're doing that. I don't see like any reason the second thing is better than the first thing. If it's just copying.
Oh, you're only copying the live data. Remember, the whole point is you're trying to collect free memory, right? So you're collecting the garbage. You're only copying over the live data when you copy over. You're not copying over everything. And so everything that was previously dead is now reusable, at least when you copy it back. So the idea is,
instead of like marking stuff free as you no longer need it,
Yep.
you just leave it in there. Because like in the little illustration, there's no like black empty spaces.
Yeah.
So you're saying the reason there are no black empty spaces is because it's not marking it as
Right.
free as it's no longer needed.
Exactly.
It's not until it copies it that it figures out.
right, there's no fragmentation at all. I don't even have to go through and mark things free and then try to compact. I think of this as you're moving apartments. You copy, you've all know, I mean, wait till you buy a house and you're in there for years and years, right? You just build up all kinds of stuff that's just there, right? When you move is a good time to move. Maybe you just move the things you care about, and everything else you just take to DI or whatever. Right? And so this is literally the case where you're just copying over the stuff you care about, the live data, and then everything else in this space is one big contiguous free block. So there's no free list or anything. There's just a pointer that says, here's everything above this is free. And then when you copy back, you don't even mark the stuff that's left here, the remnants of things that were, I mean, they're still there in the from space when you copy over. The thing is, you just don't care. You're going to start paving right back over that when you start actually using that space. Okay. So you see the basic idea. We're going to have two spaces, from space to space. We'll copy over only the live data, and that means that we spend zero work on stuff that's no longer active. Remember, mark and sweep, you've got to actually go through, not only mark the live stuff, you've got to spend work freeing up, mark the collect phase. There is no separate collect phase and stop and copy. We spend zero work on the stuff that's not reachable. Also, once you copy over, again, you have one contiguous free block of memory, and so you have, you don't have any worries about fragmentation at all. Yeah.
So what if, like, you don't have enough space to do that kind of full copy over?
So this is where I mentioned that usually, though, having a completely unfragmented half of the heap is better than having the entire heap fragmented into tiny little blocks, little slivers here and there. And so one of the key drivers is that observation or that strategy. But the other thing is, maybe this isn't all allocated at once. Maybe I just have one chunk that I've requested from the OS, and it's using this space. I could always make another request to the operating system for a whole new chunk of memory temporarily, copy everything over, and free it back up for other things on my computer to use. Remember, the heap is not the entire memory on your machine. It's only the memory that one program's using. And everything else is all the other stuff on your machine. All right, so let's look at how it works. What we're going to do is we'll start from the root set, and everything that's reachable from the root set we'll copy over. And then similarly, everything that's reachable, everything that's still otherwise reachable from those things get copied over as well. So it's the same thing as mark and sweep in the sense that everything that's reachable from the root set gets copied over to the two space. The two space is nicely compacted and everything else is free. And then everything else still sits here in memory. We don't go back and mark it free. We don't do anything else. It's just still sitting there. But then now when we switch back, we'll copy so this two space might have a whole bunch of, you don't ever, there's no way to actually clear memory. RAM is just RAM, it stores bits. And so this will still store this, when we say this is free, only in the sense that I'm gonna have a pointer here that says everything above this is fair game to be used. It doesn't mean that there isn't, ghosts and remnants of data that's still sitting there. By the way, if your language actually allows you to arbitrarily manipulate pointers and access those ghosts of deleted things, that's actually a great security hack. Okay. Sorry, great if you're the hacker, not great if you're trying to do a secure system. All right, so everything else here that's not copied over is just sitting in this from space. Everything in the from space is sitting here, unmodified except for a few things we'll get to in a minute. But then when you copy back, the whole thing's fair game. So what happens is, if you watch the pattern of usage for an incremental, or for a stop and copy collector like that, it looks a bit like this. So this is meant to be time indicated on this axis. This is the two semi-spaces. And then the vertical axis is how much of it's used. So we start off with some amount used, and that grows and grows and grows as memory allocation happens. It hits a point where garbage collection is triggered. We then take everything in here, we copy only the live stuff to the other semi-space, and then we start allocating in there. And then when garbage collection triggers in, we copy back to this space only what's used, and then continue to allocate, and back and forth and back and forth. See the idea? There's all kinds of variants with multiple spaces that you can use with this. that try to get to this issue of, well, I'm using half of it. Well, maybe one of the things I can do is I can actually structure it where I have 3. So there's always 2 that are in use and 1 that becomes a new 2 space when either of those fill up. Does that make sense? So you can use various strategies like that. So there's all kinds of things where there's multi-space variants that are not only possible, they're actually quite common. Big advantage with stop and copy is you're only spending time on the live objects. You spend 0 time, or you waste 0 time on the things that are dead. So it ranks really, it's sound, high utility, but also pretty efficient. Okay. Objects then are also immediately copied during traversal. As opposed to a separate mark and compact where I've got to go through marking and then I've got to make multiple passes through to actually do the copying. We're actually going to update the pointers while we're visiting that particular node, okay, or that particular object in the heap. So in other words, we're going to be smart about the order in which we do the copying, and if we do it right, there's no separate compact phase either. And there's no separate mark and then copy kind of thing. All the copying is happening while we're traversing